Okay, so good morning everyone. Senan this side, and in this video we are going to solve this path maximum probability. So this is the daily question for today, and clearly seeing the first sentence you know that is the problem graphs. So to do this I would assume that you know how to go and write up a code for Dijkstra's algorithm. So what I'll do is basically modify that algorithm a bit so that you could solve this problem. Either you can watch anyone else's video on the same topic, or I have made this Dijkstra's algorithm a few weeks back, so you can see that as well. But anyways, let's go and we'll also see the dry run of the code on pen and paper so that you get the idea that what exactly we are going to do. So you are given an undirected weighted graph of n nodes. Okay, so you have n nodes and it's zero based indexing. Also you are given an edge, all the edges 0 1 0 2 1 2, right, connecting the nodes a and b with the probability of success in success probability. Okay, so clearly the data types are not matching in this case, right? Edges are of different data type and the success probability is also in a different data type. So what they have done is basically given you two lists, and the ith indices in ith index of this edge and this success probability are related. Okay, so given two nodes start and end, find the path with the maximum probability of success to go from start to end and return its success probability. Okay, so if there is no path, return 0, and your answer is in the range of plus minus 1 to the 1 e to the power minus 5, so that would be accepted. Why this is given? Because floating point arithmetic in computers are basically having some rounding errors, so that is why they give this buffer of correct solution. So let's see a test case. So you are starting from 0 and you have to end at 2. So first of all, tell me what is the maximum probability one can have. Correct, that is one. What is the minimum probability that it can have, the path can have? Again, correct, it's 0. And given that, so if the probability of reaching a node is 0, that means the graph is basically disconnected, right? You cannot reach that node. Okay, so if there is a path, right, so what do you do? So given this, either what is the probability starting from the 0 node, you can reach the 0th node. Exactly, probability is 1 because you're standing at that same position, right? Now starting from 0, you can reach 1 in probability half, and 2 with a probability 0.2. But if you see, if you go from 0 to 1 to 2, you have a probability of 0.5 to reaching 1, and again a 0.5 to reaching 2, so that means 0.5 times 0.5, which is 0.25, which is greater than what we initially had, 0.2, right? So that is the thing. If you see this, you can never reach from 0 to 2. In this case, the output would be 0. You can reach 2 at 0 to 2 as at max at 0.3, because if you go by this route, you will have the maximum probability as 0.25. So before getting into the problem, I understand to reach from 0 to 2, the path, you multiply all the probabilities in that path to get the total probability. So going from 0 via 1 to 2, you get 0.5 times 0.5, which is 0.25, and from 0 to directly to 2, it's 0.2. So maximum of these two is 0.25. That is the whole point. Similarly, in this second case, we are, while traveling via 1, we have a probability of 0.25, but if we go directly, we have a probability of 0.3. So maximum is 0.3, and that is return. So now if you remember Dijkstra's algorithm, we used a min heap, right, to find the minimum. But in this case, what we can do is tweak that algorithm a bit, and we say rather than using a min heap, we are going to use a max heap. Why max heap? Because the maximum value, the upper bound of the probability is bounded by 1. You cannot have a probability more than 1, nor you can have a probability that is less than 0, right? So this value of probability is in the sweet spot of 0 to 1, and that is why I can use this logic of Dijkstra but with a max heap. Okay, so let's first of all look at the dry run for this first one and this second one, and then we'll see how do we actually code that. Okay, so here we are at our notebook, and as you can see, the start point is this, the ending point is this. Now I keep a visited array and I initialize the probabilities as 0, right? Why do I initialize it that way? Because assuming that we cannot reach any node, that is the base assumption. Okay, so what I do, is, first of all, I initialize this visited array and this max heap. So what I do is I say the probability of reaching this start node, which is the 0th node, is what? Is 1. So I'll take this and I'll make this as 1. That is the maximum probability you can have. And after doing this, what I'll do is I'll push the probability and the node itself. This is storing probability comma the node. Now we actually do the Dijkstra's algorithm. What I'll do is I'll pop this out and I'll see all the neighbors, right? I'll see this neighbor and this neighbor. So my current node equal to 0, my probability is equal to 1. This is fine. Now what I see is the edges or the neighbors of this node, right, which are having a probability greater than this. So I see 1, I see a 1, right, and I see the probability of reaching this is what? 1 times 0.5, that is 0.5 itself. So I can reach 1 at a max probability of 0.5. But when I see what I have known till now is I can reach that with 0 probability. So that means there is an update that should be made. So I'll say that this is not 0, I'll say this is 0.5. Okay? And after I do that, I'll push the new element in the heap. So I'll push this node 1, and which had a probability of 0.5. Okay, good. Now I have processed this neighbor. Now I'll go and process this neighbor. Now what I see is, okay, I can reach this 2 at a probability of 1 times 0.2, that is 0.2. I can reach this with probability 0.2, and what I have currently in my visited array is 0. That means this is a better path, or a path with a higher probability. So what I would do is I'll take this, I'll cancel this out, and I'll say this is 0.2. And doing this, I push that into my max heap, and the probability is 0.2, and the node is 2 itself. Okay, now we are done with this first pullout of this heap element. Now since this is a max heap and it is sorted on the basis of the probability, right? So now I'll take out the maximum element, that's 0.5 and 1 thing. Okay, so what I'll do is I'll take this out and I'll say the node is now 1 and probability is 0. Now what I do is I'm currently here, right, and I see this neighbor. So I can reach, starting from this with probability 0.5, I can take this edge and reach 0 with a probability of 0.5 times 0.5, which is 0.25, which is less than this. So that means this is not a good path to go to 0, because I have already a path with a higher probability. So I don't do any update. Now I see the next name. I see this 2. So I can reach this 2 with a probability of 0.5 times this edge. So 0.5 times 0.5, which is 0.25. And now if you see, this 0.25 is greater than 0.2. That means we have found a path to reach 2 that is better than what we had previously found. So what I do is I do the update 0.25, and now what I do is I push that into my, because I've made a change, right? I've made an update 0.25 and the node itself is 2. Now we are done with this first node, so I'll just cancel that out. Now what is the maximum element in this? This is based on the probability value, which is this 0.25, right? So what I do is I make this node as 2 and the probability is 0.25. And now what I see is, let's look at all the neighbors of this node, which is this. I see this, right? So what I'm saying is I can reach this node 2 at probability 0.25, and now I can reach 0 by taking this route and with probability 0.2 times 0.25. So 0.25 times 0.2 is what? 0.05, right? That is what I think. So that is obviously lesser than this one. So I don't perform any update. This is not that of a good route to reach 0. Again, now I see the next neighbor, which is 1. I see I can reach 1 as 0.25 times 0.5. So I can reach 0.25 with probability 0.25. I can reach 2, and multiply that by 0.5. I can reach 1. So 0.25 times 0.5 is equal to 0.125, which is already lesser than this. So that means this is not a good path to reach 1 itself. So what I do is I'm done with this out. Now the next element is 2, probability 0.2. Now technically it would go and check all the neighbors of this 2, perform the same update, But if you see, we did this with 2 just before now and we did not get any updates, and the value of probability is higher than what we have here. That means in the end this won't be doing an update. So what I do is I just pop this out and our heap is empty. I get out of this loop and I return the value of visited of 2 because this is the end node, right? So this value is 0.25. That is our answer. Now let's do this for when the case for the case of where this was 0.3. We'll do this again, but we'll do it faster. So anyways, 0 is the start, right? So what I do is I initialize this probability 1 and start node as 0. Now I initialize this visit as 1, right? Now after this I pop this top element, right? If I remove this, I would have my node as 0 and probability as. Now I look at all the neighbors. I see I can reach 1 with a bit probability, that is 0.5. So what I'll do is I'll update this 0.5. I'll add that to my priority queue and this. Now similarly I would see my right child of this or the next neighbor, which is 2, and I can reach this with a probability of 0.3. So what this would do is I'll have to make an update 3 and 2. Now I'm done with this node and 0. Now what I do is I take the top element. So my new values would be node is 1 and probability is 0.5, and I cancel that. Now if you do the calculations, neither this or this would give you a better result, so you'll just pop this out. And similarly for the last node 0.3, you take this out, you won't get a better path from this. So again, you'll pop this. I've shown you how to do the calculation, so I'll just be skipping that part, and this is what you get in your answer. So what you do is you return the value at this second node, second location in this, which is 0, 1, 2. So you return 0.3 as your answer. So this was the whole logic, and let's see how do we actually implement this in code. So this is the whole code, and how do I proceed by this? First of all, I created an adjacency list for me because that allows us for easier traversal of the graph. So I have a pair of int and the probability as it. So node and the probability, right? Now I go through all the edges and I say the first node, I get out the first node, I get out the second node, and I get out the probability. So for node 1, node 2 is a neighbor with probability this, and for node 2, node 1 is the neighbor, right, with probability this. Now what I do is I initialize a visited array, which would also at the same time store the value of probability. Although you can have a separate visited and probability array, I find that we can do it in a single array. That's more than enough. And what I do is I say that the start node is initialized with 1 because reaching that start node has a probability of 1. Now again, we have a max heap, not a min heap like the extras. We have a max heap, and the first would be storing the probability and the second one node would be storing the node. So I have written like this is because while comparing the elements, it would do the comparison of probability rather than the nodes in the priority queue. That's just the syntax. Now I push the first node with probability as 1. Now till the time this priority queue is not empty, I take out the current probability, current node, and remove that from this, what do I say, this max heap. Now I traverse to all the neighbors. I find the neighbor and their edge probability, and I find out the new probability. New probability is whatever it got me to reach this current probability, current node, and whatever is the edge probability. So that is my new probability for reaching this new node. So if visited of this node child is less than new probability, I just update that with the new probability. And since I've made an update, I need to push that into my priority. And in the end, till the time I do this, VQ is not empty, and in the end I return the visited end node. Let's say we never arrived or the graph is disconnected. We were not able to get to this node 2. That means since we had already initialized this to 0, anyways our answer would be stored in this end node. So some things, the test cases are running well and fine. See, it is also accepted, solution is also, and yep, that was the video all about. The time complexity, space complexity is exactly what we had in breadth first search or the Dijkstra's algorithm. Let's go over through this once. So this priority queue can be storing every element in the worst case, so that is big O of n. Visited array is also big O of n, and For this, for storing this adjacency list, we have big of v plus 2e in a way, right? Big of v plus elements, because for every edge we are pushing two values into the adjacency list. So that is the space complexity. The time complexity is we would be visiting every node, right? So big of v plus e in a way, v plus 2e if you want to. So the time and space complexity would be big of v plus 2e, where v is the number of vertices, e is the number of edges. Really, this is what it is, right? So yeah, that was the whole video all about. Hope was helpful, the whole solution, right? I hope this was helpful, and I'll see you in the next video.